The periodicity of elements refers to the repeating trends in chemical and physical properties that appear when elements are arranged in order of increasing atomic number. This regularity arises from the systematic filling of electron shells and subshells, which determines an atom's electron configuration. As we move across a period from left to right, the number of protons in the nucleus increases, leading to a greater effective nuclear charge. This stronger attraction pulls electrons closer to the nucleus, causing atomic radius to decrease, while ionization energy and electronegativity generally increase. In contrast, elements in the same group share similar valence electron configurations, which explains why they exhibit similar chemical behaviors, such as forming ions with the same charge or participating in similar types of reactions. Moving down a group in the periodic table, additional electron shells are added, increasing the distance between the valence electrons and the nucleus. As a result, atomic radius increases, while ionization energy and electronegativity tend to decrease because outer electrons are more easily removed. These vertical trends explain systematic changes in metallic character, reactivity, and bonding behavior across the table. For example, alkali metals, such as lithium and sodium, become more reactive down the group. Understanding periodicity allows chemists to predict the properties and reactivity of elements, even those that have not been extensively studied, making the periodic table a powerful organizational and predictive tool in chemistry. This slide introduces Dmitry Mendeleev, often called the father of the periodic table, and highlights why his work was revolutionary to chemistry. Mendeleev was a Russian chemist who lived from 1834 to 1907, a time when many elements were known, but there was no coherent system to organize them. Chemists had measured properties such as atomic mass, density, and reactivity, yet these facts seemed scattered and disconnected. Mendeleev's genius was recognizing that these properties were not random. By carefully arranging elements in order of increasing atomic mass, he discovered that certain chemical and physical properties repeated at regular intervals, a concept we now call periodicity. What made Mendeleev's contribution truly remarkable was his willingness to trust these repeating patterns over incomplete data. As he organized the elements, he noticed gaps where no known element fit the pattern. Instead of forcing the table to accommodate existing knowledge, he boldly left these spaces empty and predicted the existence and properties of undiscovered elements. In several cases, such as elements later known as gallium and germanium, his predictions were strikingly accurate. This demonstrated that the periodic table was not just a way to organize information, but a powerful scientific model capable of making reliable predictions. Mendeleev's work laid the foundation for the modern periodic table and transformed chemistry into a predictive science, allowing chemists to understand and anticipate the behavior of elements based on their position in the table. Electrons in an atom reside in electron shells denoted as N1, N2, N3, and beyond, and they occupy specific energy levels around the positively charged nucleus. These energy levels are called orbitals. Electrons may be excited to higher energy orbitals when they absorb energy, represented as h-nu, or they may relax to lower energy orbitals when they release energy. An electron shell may contain more than one orbital. An orbital diagram is a visual representation showing how an atom's electrons occupy orbitals, often illustrated by lines or boxes. Here is how orbital diagrams are constructed. The first electron shell contains only the 1s subshell, which has one orbital. The second electron shell contains the 2s and 2p subshells. The 2s subshell has one orbital, just like the 1s subshell, while the 2p subshell has three orbitals. The third electron shell contains the 3s, 3p, and 3d subshells. The 3d subshell has five orbitals. In general, an s subshell has one orbital, a p subshell has three orbitals, and a d subshell has five orbitals, regardless of the principal electron shell. In the next slide, I will show how electrons are placed into empty orbitals, following the appropriate filling rules. This slide illustrates the periodic patterns of valence electrons, which are key to understanding the chemical behavior of elements. The orbital diagram constructed in the previous slide is shown here. Valence electrons are the electrons located in the outermost electron shell, also called the valence shell. These electrons determine how an atom bonds with other atoms, how reactive it is, and what types of ions it tends to form. Hydrogen is the first element in the periodic table, and its atomic number is 1, meaning it has one proton. Consequently, a neutral hydrogen atom has one electron to balance the charge of the proton. The electron configuration of neutral hydrogen is written as 1s1. Here, 1s labels the 1s subshell, and the superscript 1 in red represents the single electron of the hydrogen atom. The atomic number of helium is 2, so it has two electrons to balance the charges of the two protons in its nucleus. Note that no more than two electrons can occupy the same orbital. When two electrons share one orbital, they must have opposite spins. This is known as the Pauli exclusion principle. The electron configuration of helium is written as 1s2. The atomic number of lithium is 3, so it has 3 electrons. Since a single orbital can hold a maximum of 2 electrons, the third electron in lithium occupies the 2s orbital. The electron configuration of lithium is written as 1s2, 2s1. The atomic number of beryllium is 4, so it has 4 electrons. The electron configuration of beryllium is written as 1s2, 2s2. The atomic number of boron is 5, so it has 5 electrons. The electron configuration of boron is written as 1s2, 2s2, 2p1. The atomic number of carbon is 6, so it has 6 electrons. Keep in mind that when electrons occupy multiple orbitals of the same energy within a subshell, they first occupy each orbital singly with parallel spins before any orbital is doubly occupied. This is called Hund's rule. The electron configuration of carbon is written as 1s2, 2s2, 2p2. The atomic number of nitrogen is 7, so it has 7 electrons. The electron configuration of nitrogen is written as 1s2, 2s2, 2p3. The atomic number of oxygen is 8, so it has 8 electrons. The electron configuration of oxygen is written as 1s2, 2s2, 2p4. The atomic number of fluorine is 9, so it has 9 electrons. The electron configuration of fluorine is written as 1s2, 2s2, 2p5. The atomic number of neon is 10, so it has 10 electrons. The electron configuration of neon is written as 1s2, 2s2, 2p6. The atomic number of sodium is 11, so it has 11 electrons. The electron configuration of sodium is written as 1s2, 2s2, 2p6, 3s1. Finally, let's consider argon, which is located on the far right of the periodic table. The atomic number of argon is 18, so it has 18 electrons. The electron configuration of argon is written as 1s2, 2s2, 2p6, 3s2, 3p6. This slide explains the difference between a full electron configuration and a condensed electron configuration. Electron configuration describes how electrons are distributed among the orbitals of an atom, and it follows a predictable order based on increasing energy levels. As illustrated in the previous slide, in a full electron configuration, every occupied orbital is written explicitly, starting from the lowest energy orbital, 1s, and proceeding through higher energy orbitals such as 2s, 2p, 3s, 3p, and 3d. As shown in the previous slide, the full electron configurations of lithium and sodium should be written as follows. The electron shells other than the outermost shell are called core shells. 1s for lithium, and 1s, 2s, and 2p for sodium. The outermost shells are the one with the highest N number, and they are called valence shells. 2s for lithium, and 3s for sodium. These electron configurations show that both lithium and sodium have a single electron in their valence electron shells. Note that valence electrons primarily determine the chemical behavior of an atom. An interesting observation is that the core shell electron configuration of lithium is identical to the electron configuration of helium. Helium is a chemically inert noble gas. Likewise, the core shell electron configuration of sodium is identical to the electron configuration of neon, which is also a noble gas. The condensed electron configuration provides a more efficient way to write electron configurations by replacing the core electrons with the symbol of the nearest preceding noble gas, shown in brackets. Because noble gases have filled and stable electron shells, they serve as a convenient reference point. In the condensed notation, lithium and sodium are written in this form, indicating that the core electron configuration of lithium matches that of helium, and that the core electron configuration of sodium matches that of neon. This condensed form shows both lithium and sodium has the same valence electron configuration, which explains why they exhibit similar chemical properties. The condensed electron configuration highlights the valence electrons more clearly, making it especially useful for understanding periodic trends, predicting reactivity, and analyzing bonding behavior. Both representations describe the same electron arrangement, but the condensed electron configuration emphasizes the most chemically important electrons while simplifying the notation. This slide highlights the periodicity of elements, emphasizing how repeating patterns in electron configuration explain trends in reactivity and chemical behavior across the periodic table. The organization of elements into groups reflects similarities in their valence electron configurations, which directly control how atoms interact. Note that only valence electron configuration of each element is shown in the table. At the far right of the periodic table are the noble gases, which have a complete valence shell described by Ns2 and P6, except for helium, which has a stable 1s2 configuration. Here, N represents a positive integer, 1, 2, 3, and beyond. Noble gases are largely unreactive and have low potential energy because their valence shells are full. This slide reinforces a central idea of periodicity. Elements that do not already have a noble gas electron configuration tend to react by losing, gaining, or sharing electrons to achieve one. On the left side of the table are the alkali metals in group 1A characterized by an NS1 valence configuration. These elements, such as lithium, sodium, and potassium, are soft enough to be cut by a knife and highly reactive because they readily lose one valence electron to achieve a stable noble gas electron configuration. Their high reactivity, softness, and tendency to form +1 ions are all consequences of this single, loosely held valence electron. Just to the right are the alkaline earth metals in group 2A, which have an NS2 valence electron configuration. These elements are still reactive, though less reactive than alkali metals, because they must lose 2 electrons to attain a noble gas electron configuration, forming +2 ions, such as beryllium 2+, magnesium 2+, and calcium 2+. On the right side of the periodic table, the periodicity of nonmetals is evident. The halogens in group 7A have a valence configuration of Ns2Np5, meaning they are just 1 electron short of a full valence shell. As a result, they are the most reactive nonmetals and tend to gain 1 electron to form -1 ions, such as F-, Cl-, and Br-. This repeating pattern of electron configurations across the periodic table explains the predictable trends in reactivity, ion formation, and chemical properties that are fundamental to understanding chemistry. This slide explains the formation of cations and anions, showing how atoms gain or lose electrons to achieve a more stable, noble gas-like electron configuration. Atoms are electrically neutral when the number of protons equals the number of electrons. However, many atoms become more stable by changing their number of electrons so that their valence shells are either completely filled or emptied. This process leads to the formation of ions, which are charged particles. When an atom loses electrons, it becomes cation, a positively charged ion. When an atom gains electrons, it becomes an anion, a negatively charged ion. The driving force behind ion formation is the tendency of atoms to reach a noble gas electron configuration, represented as Ns2Np6, or 1s2 in the case of helium. On the right side of the periodic table, nonmetals typically form anions by gaining electrons. For example, fluorine has an electron configuration that is just 1 electron short of a full valence shell. By gaining 1 electron, fluorine becomes the fluoride ion, F-, with a stable noble gas electron configuration, identical to neon. Similarly, oxygen has the configuration that is 2 electrons short of a full valence shell and gains 2 electrons to form the oxide ion, O2-, also achieving a noble gas configuration. Sodium, with a valence configuration of 3s1, loses 1 electron to form Na+, revealing the stable neon core. Now, pause the video and show the ion formation of calcium and nitrogen in the same way as fluorine, oxygen, and sodium. Use condensed electron configurations and show how the valence electron configuration changes as each ion forms. The answers are as follows. This slide summarizes the formation of cations and anions across the periodic table by highlighting the most common ionic charges formed by main group elements. The key idea is that atoms form ions to achieve a stable noble gas electron configuration, usually by losing or gaining valence electrons. The table is organized by groups, making it easy to see repeating patterns in ionic charge that reflect periodicity in electron configuration. Metals on the left side of the periodic table tend to lose electrons and form cations, while nonmetals on the right tend to gain electrons and form anions. Now, please complete the lab worksheet posted on D2L to reinforce our understanding of the periodic properties of atoms.